So continue a little bit on mass transfer in laminar flow, which is refers to boundary layer flow on a flat plate. Okay, by considering the flow of fluid B over a thin flat plate parallel with the direction of flow of the fluid upstream to the plate as shown in figure 3.14, it is refers to laminar boundary layer development for flow across a flat plate. Okay, let the fluid velocity profile upstream of the plate be uniform at a free system velocity U naught. Okay, this one. Okay, U naught, U naught, U naught. U naught is increasing with the increase of elevation or direction. So, as the fluid passes over the plate, which is fluid from this direction to the right, okay, it passes over this plate, the velocity of ux, which is refers to this one, okay, in the direction of flow is reduced to 0 at the wall, which establish a velocity profile due to drag. At a certain distance z, normal to and out from the solid surface, the fluid velocity is 99% of u naught. This distance, which increases with the increasing distance of x from the leading edge of the plate, is defined as the velocity boundary layer thickness del. So the build-up of this layer, okay, the velocity profile of the layer and the drag force can be determined for laminar flow by solving the equation of continuity and motion, which is refers to Navier-Stokes equation for x direction. And as for a Newtonian fluid of constant density and viscosity, the absence of pressure gradient in x and y direction, which is normal to x and z plane direction, this equation for the region of boundary layer S refers to this equation. Okay, equation 3.124 and equation 3.125, where these two equation has the limitation, which is the boundary condition is ux equals to u naught whenever x is equals to 0 for z is higher than 0, and when ux is equals to 0 at z is equals to 0 for x is higher than 0, and for ux is equals to 0 at z is equals to infinity, it is for x is higher than 0, whereas the uz is equals to 0 and z is equals to 0 for x is higher than 0. The result in terms of local friction factor Fx is a local shear stress at the wall tau W, and a local drag coefficient at wall CdX is refers to this equation. So this is the relation between the local drag coefficient with the local friction factor, which is Fx, where we know that the Reynolds number, the relation is x u naught del density over mu. Thus the drag is greatest the leading edge of the plate, where the Reynolds number is smallest. When the Reynolds number is lesser, the CDX will increase, and also the friction will increase. The average value of the drag coefficient are obtained by integrating this equation from x is equals to 0 to L, and by integrating this equation, then we will get this equation as the result. So CD average over 2 is equals to 0.664 over NREL 0.5. The thickness of the velocity boundary layer increases with the distance along the plate according to the figure previously. So del over x is equals to 5.96 over Reynolds 0.5. A reasonable accurate expression for the velocity profile was obtained in Folsen, okay, who assumed the empirical form ux is equals to these values, and if the boundaries condition for this one, okay, according to this condition, and then we can state and we can use this equation. And applying the evaluate C1 and C2 from the equation will result ux over u naught is equals to this equation, where this solution is only valid for laminar boundary layer, which experiment persists to Reynolds number is equals to 510 to the power of 5 only. If the rate of mass transfer is very low, the velocity profile are undisturbed. So the solution for analogous problem, which is refers to heat transfer, which is obtained with Reynolds number is higher than 0.5. Okay, the result of mass transfer, we can use the correlation between the Schmidt number, Reynolds number, Sherwood numbers, okay, by using this equation. where we know that the relation of Sheward number and diffusivity coefficient, whenever the Sheward number is increased, the diffusivity coefficient will decrease and the coefficient for mass transfer will increase. And the driving force for mass transfer, as usual, CAI minus CA naught, the concentration at inlet, okay, minus the concentration at outlet. The concentration of boundary layer where essentially all the resistance to mass transfer residue is defined. So actually this equation is the resistance of the mass transfer, okay, is equals to 0.99, and the ratio of the concentration of boundary layer thickness del C to the velocity boundary thickness del is refers to this equation, where we can say that when the Schmidt number is higher than 1, the concentration of the boundary layer builds up more slowly than the velocity boundary layer. For a gas boundary layer, okay, that is for liquid layer. For the boundary gas layer, when Schmidt number is approximately equals to 1, the two boundary layers build up at about the same rate. Using the analogy from 3.130, the concentration profile will be given as this equation. So the equation 3.132 give the local Sheward number. If the expression is integrated over the length, okay, when we integrate the equation 3.132 over the length of the plate, which is L, the Sheward number will be like this. Okay, then we'll get the Sheward average 0.664 and Reynolds number 1/2, Schmidt number 1/3, where the Schmidt number average values is this equation. So let's do the example 3.14. Air at 100 degrees C at 180 m and a free stream velocity 5 meter over second flows over 3 meter long thin flat plate of naphthalene, okay, causing it to sublime. A. Determine the length over which a laminar boundary layer persists. B. For the length, determine the rate of mass transfer of naphthalene into air. And C. At the point of transition of boundary layer to turbulent flow, determine the thickness of the velocity and concentration boundary layers. So some of the assumption has been given for this example, which is the vapor pressure of naphthalene is 10 torr, the viscosity of air is 0.0215 cp, molar density of air is these values, and also the diffusivity of naphthalene in air is given. So by determining the length of over which a laminar boundary layer is by using this equation, okay, from equation 3.127, we know that L is equals to mu and Rex over U rho P. So you just need to substitute all of these values into the equation. The values all given from the example, so you just need to substitute, and don't forget to write down the units, okay, and then do the unit cancellation. Then you will get X is equals to 2.27 meter, at which transition of turbulent flows begin. For the length, determine the rate of mass transfer of naphthalene into air. Ca naught is equals to 0, and how to get CAI is 10 multiply with 0.0327 over 260. Why we need to divide with 760? Because we want to standardize the unit, okay? So then we will get 4.3 times 10 to the power of minus 4 kmol over m3. So from equation 3.101, which is refers to Schmidt number, and Schmidt number is equals to mu rho dAb, you just need to substitute mu. From the equation, they give you 0.0215, okay, times 10 to the power of minus 3, okay, over rho is given, dAb is also given. So you will get the value for Schmidt number 2.41. And from the equation 3.137, which is to calculate the Sheward number, then you just need to substitute the Sheward numbers and you will get the Sheward numbers 630. And from equation 3.138, you will get the value for Kc average by substituting all of these values, okay, 2.61 times 10 to the power of minus 3. And for the width of 1 meter, meaning A is equals to 2.27 meters square, and A is equals to this equation then you need to substitute the value for A and K, C average, and also CAI, CA0 from the question. Then you will get Na 2.55 times 10 to the power of minus 6 kmol per second. So Na is the molar flow rate. So at the point of transition of boundary layer to turbulent flow, determine the thickness of the velocity and concentration of layer. So the thickness will be in meter, and the concentration will be in concentration units in boundary layers. So from 3.1 to 9 at x is equals to L, okay, which is you calculated 2.27 in a previous solution, okay, which is this one, 2.27. By using that value, okay, substitute into del equation, then we will get 0.0111 meter. And from equation 3.15, you will get the del C, okay, which is refers to the thickness of the velocity is refers to del, thickness of the and the concentration boundary layers is refers to del C. You just need to substitute, okay, 0.011 over 2.41, 1 over 3, then you will get dc. So this 2 refers to thickness of velocity, del C is refers to the concentration boundary layers. So mass transfer in laminar flow, which is in fully developed through a flow in straight circular tube, we'll discuss in this chapter. Okay, so you can go through to this solution, okay, to this example or to this figure, which is this figure 3.15 is refers to build up of a laminar velocity boundary layer for flow in a straight circular tube, where this figure shows the formation and or we call it as build up of laminar velocity boundary layer when a fluid flows from a vessel into a straight circular tube, and with the entrance plane A, okay, the velocity profile is flat at this moment, and whenever the velocity is increased, okay, it begins to build up as shown in planes B, C, D and E. Okay, in this region, the central core outside the boundary layer has a flat velocity profile where the flow is accelerated over the entrance velocity. And finally, at E condition, okay, the boundary layer fills the tube. From here, the velocity profile is fixed and the flow is said to be fully developed. So at the condition A, B, C and D is not really steady state, okay, but at condition E, it is steady state, where we can say that the flow is ready or the flow is fully developed. The distance from plane A to plane E is the entry region. For fully developed laminar flow in straight, which is refers to flat condition E, the circular tube by experimental Reynolds number is denoted as NRE is equal to dux rho over mu, where ux is the flow average velocity in the axial direction, and d is the insert diameter of the tube, okay, and d is much less than 2100. For this condition, the equation of motion in the axial direction of the horizontal flow and constant properties will be like in equation 3.139, where the r is equals to 0 for the axis of the tube, r is equals to rw for the tube wall, and for ux is equals to 0, and the dux over dr is equals to 0. So the equation 3.139 was integrated, okay, by this man, okay, and this man. The resulting equation for the velocity profile is expressed in terms of this equation and in terms of maximum velocity at the tube axis. From the equation 3.141, the velocity profile is parabolic, since you see this is square r over rw square. So it can say that it is the parabolic in nature. The shear stress or the pressure drop, the fanning friction factors are obtained from the equation 3.139, okay, with the condition of F is equals to 16 over NRE. And LE over D is equals to 0.0575 and Reynolds number, where this LE is actually the axial distance, and D is the diameter. And the analog species continuous equation for mass transfer by neglecting the bulk flow. So this is the relation for an